get started. My name is Collin Wilkinson, and today I'm going to be talking about AI, materials. Oh, oh, hi, Henry. Thank you. Um, so today I'm going to be talking about AI, materials, and the Earth, and about how we can get better faster. I'm a recent PhD. I just got my PhD like a month and a half ago. So this is my first kind of one of these talks. So please stick with me, and I hope you enjoy it. Um, so I've divided the talk into sections, as you do. And so these sections are just going to be telling you about um, the history of materials or the history of mankind, according to a materials engineer. Uh, no guarantee that this history is correct, is just the way I view it. We're going to talk about chemistry, and we're going to talk about finding replacements through modeling, and we're going to talk about AI, and then I'm going to talk a little bit about how I see the future and how some of my colleagues see the future. So starting with history, in the beginning, there were rocks and gods, and that's pretty much true to this day. In the beginning, these things were true. To this day, it's true. And that's kind of how mankind has viewed things, right? We have materials and we have religion. Um, Not overly simplified at all. It's just a little viewpoint. And so we can start to break down kind of the tech tree of mankind. And so, of course, in the beginning, we had rocks. And in this early period of mankind, what we did was we had found materials. And what I defined as a found material is something that we just found in nature and figured out how to use. And so this is what defines the Stone Age, right? And so our found materials came in pretty much two different types. We had obsidian, or not, sorry, that's not one of the types. We had inorganic and organic found materials. So things that were alive and no longer alive or came from animals, and things that naturally occurred. So in this case, the representative of our inorganic is this black rock here. Let me get my marker. Yeah, yeah, good. Laser point. Cool. So this is our example of an inorganic material, which is obsidian, which is a naturally occurring glass. And then we have our organic material, and this would be like silk. This would be furs. It would be uh, different animals, and these kind of things really defined the early Stone Age. Um, and around the turn of the Stone Age, when we really started getting built and civilized, we uh, we started experimenting, right? And we realized very early on that we could make even better stuff by experimenting. And one of these great stuff that we discovered early on was beer, as well as many other baked goods such as bread. And so around this time, we started experimenting with stuff besides food as well, right? So then we went into this new age where we no longer had just found materials, but we also started synthesizing materials. And so very early on, we started producing glass, right? We had seen this obsidian, we saw how valuable it was, this naturally occurring glass. And somebody at some point realized that we could also produce an artificial version by just melting some rocks with a little bit of salt. And we were able to produce um, glass this way. We also started refining metals a little bit, right? We were able to realize that if we mix these two different kinds of rocks, we were able to uh, get some new unique materials. And same with ceramics. So this became our early period of discovery. And past that, we had another era. And this era was purification. So we had found materials, mixed materials or processed materials, and then pure materials. And so these pure materials, gold, iron, silver, are pure elements that we realized that we could distill from other things that we found in nature to its most pure form. of course, we didn't realize what elements were at that time. So instead, that came later. Before we move on, I just want to stop and talk about my love of glass. I am a glass scientist by training. My specialty is in glass. I am a work at a startup company uh, that focuses on glass. And what's so cool about glass is that it's this ancient material that we're constantly finding new uses for. And I'm going to go into this in a little bit, but you might see like a common glass centric theme throughout the presentation. And I just wanted to let you know that it's not just because, I mean, glass is amazing and is the world's most important material, but it is also because of my own personal bias creeping in, because who doesn't love glass? It's pretty, it's functional, it's great. So moving on from here, we could even start to understand these ancient cultures and these ancient religions through their practice of making materials. So this is the earliest recording of glass making in all of history. 3,300 years ago in Mesopotamia. And there's some great lines in here, right? You got to have a kubu images in there. You got to have religious images. You got to have a favorable month for a great day. And then you must make a sheep sacrifice. I have to tell you that I no longer make glass this way. I make glass without the sheep sacrifice, but I do keep the kubu images there just for good luck. And of course, I pour out the libation of honey and liquid butter, because why would you not? So around this time, we also started gathering a tech tree for smart people. And at first, smart people only came in two flavors, right? We had philosophers and we had doctors, right? We had people who would think about the world and people who would heal other people. And for a while, that's pretty much how it remained. And then in the Middle Ages, we started to have alchemists, sorry, wrong alchemist. We started having alchemists who were people who were trying to play with the natural order of things, who were trying to build an understanding. And eventually this alchemy, or natural philosophy, as they were called, also split into two different sections. And these two different sections were essentially physics and chemistry. So in terms of physics, it depends where you're from, who you consider to be the first physicist. If you're from the Middle East, you would consider Al-Kindi to be the first physicist. If you're from England or the English-speaking part of the world, which many of us consider Isaac Newton to be the first physicist. If you're from Italy, you would fiercely disagree and you would argue it was Galileo Galilei. And if you're from Denmark, you would argue that it was Kepler, Johannes Kepler, who was an interesting guy. All of these people were very interesting people. And then in terms of chemistry, it's generally agreed that Robert Boyle of Boyle's law. So if you've ever heard of ideal gases, it all kind of comes derived from Robert Boyle. And so this is kind of our modern division, right? We go to philosophers, to alchemists, to physicists and chemists. And we kind of have these higher degree of divisions as life goes on. And all of these groups of people, these people were essentially trying something, experimenting with it, and then trying to write down some universal acknowledgement, right? And there's great stories about all of them doing that, right? Tycho Brahe was actually really struggled because what he found mathematically did not match with what his religious experience told him. So he actually ended up giving up part of his religious beliefs to make it work with his own mathematics. And so that's one of the first real centric moments in science, was Tycho Brahe realizing this. And so these people continued their work, and the evolution of the fields went along with them. So along this time, alchemists were doing a lot of different work. And one of the beautiful things that they did was they started coloring glass, stained glass, either by painting it or by changing the chemistry. And this is really important because they realized that by slightly changing the amount of stuff you could put in a material could radically change the properties. So for instance, a blue glass has about 1% cobalt. That's it. It's the same as most of the other glasses, but it has got 1% cobalt, not 1% cocoa, in like it says in the text. That'd be very different. And so what they realized was changing these small chemistries can make big differences. And so these kind of same questions are directly what led to investigations of later scientists into the nature of the universe, the nature of materials. And so the modern study of nature and materials really begins with this guy, Mendeleev, who put together the periodic table. And he was actually a chemistry teacher who wanted to write a textbook because he hated all the other textbooks. He thought they were so dry, so useless. He was just done with them. And what he realized was that if you arrange the elements in a certain order, there were definitive trends. If you put them in order of their mass, there were definitive trends. And so thus he concluded that these were fundamental substances some way, and that these fundamental substances were basic and were made up large amounts of the planet. And so this was rather revolutionary. And at the time, no one believed in atoms, right? You have to realize that atoms were a very controversial topic. It's like string theory today, right? Some people believe it, some people don't. Most people don't really care. Atoms were just something that didn't exist. And people continued to disbelieve in atoms. However, there were a few scientists who were really devoted to the idea, who did fundamental work that built our modern understanding of what an atom is and what a material is. And so what I mean when I say a material is an assemblage of atoms that produces something solid. That's it. And there's a wide range of materials. And today I'm going to focus mostly on the inorganic ones rather than the organic ones. If you need an organic one, I would recommend go talking to a biochemist or a biologist. Whenever there's carbon involved, I just peace out. I just zone out. What can I say? Not a carbon fan, besides, living, I guess, but whatever. So Boltzmann is probably the father of modern atomistic science. And he was brilliant beyond his years, but he also suffered a lot from depression, and he was not very well liked in the scientific community because he was just kind of like a chill guy. He was quiet. But he just wanted to know, if atoms existed, what would the universe behave like? And so he started deriving all this math. And what he realized very quickly was you can't absolutely say what the behavior of an atom is on a large scale. Instead, you have to realize it through statistics. And this made him even more of a social pariah, because the only thing statistics were used for in the late 1800s was for gambling. And you also have to realize how religious a lot of Europe was around the same time. So Ludwig von Boltzmann just started using statistics in science. And people were not a fan. Particularly was this one scientist named Ernst Mach. I think many of you will recognize the name Mach speed, like the speed of sound. So if you're going like 2 times the speed of sound, it'd be like Mach 2. And Mach was a huge advocate of being, if you can't see it, it won't affect you. And he was the most dominant voice in all of European science, particularly German and Austrian science at that time. And big names followed him. Like Einstein, when he was an undergraduate, learned about Mach's theories. Uh, he uh, he really struggled uh, to be able to fit in. Boltzmann did, and Mach just relentlessly tormented him for his belief in atoms, because Mach thoroughly believed that if you can't see it, there's no point. Of course, this is incorrect. We now know that atoms dominate most of our life. And so Boltzmann ended up actually killing himself after he published his few revolutionary papers that no one realized at the time. In fact, because he died through suicide, they put him in a grave that was, not fit for anyone. Uh, but later on, when they realized how important it was, mostly to Einstein and especially this guy named Planck, advocating for his work, the government of Austria exhumed his body and reburied him here with a bust of his face. The other phenomenal player that really helped atoms come to realization was Marie Curie, and to a lesser extent, Pierre Curie, her husband. And Marie Curie was studying radiation at the time and was realizing that there were high energy particles coming off groups of materials. And the only way that she could figure out how that was happening was that there had to be sources of high energy inside a local region, which she believed correctly was very convincing evidence for atoms. So these two really did a ton of phenomenal work that led to atoms being discussed worldwide. Um, if you ever get a chance, I would highly recommend reading Marie Curie's biography. It's very interesting. It stretches from like affairs that go onto the front page of Paris newspapers to her building X-ray machines and inventing chemotherapy, um, and going into World War I with her daughter. Really incredible person. Uh, and then after this came Einstein, came, uh, I'm sorry, Schrodinger, and of course Heisenberg. Wrong Heisenberg, right? Okay, so you got Heisenberg and Bohr here. And many of you will recognize these names. And these kind of people really laid even more foundational work for the idea of quantized matter. In particular, Schrodinger and Heisenberg developed the Schrodinger's equation and Heisenberg's uncertainty principle. I'm sure you guys have heard about his cat and his principle. And what they really say was that it's not just, matter that's quantized. Everything can be quantized. Sometimes, but when we quantize it, we also have to consider that it could be a wave. And so everything can either be a wave or a particle. It depends how you look at it. Heisenberg himself was a very sad story. Well, not sad, messed up story. I guess Bohr is the one who has the sad story. Heisenberg really attached to Bohr at an early age, like early 20s, and they published together and were inseparable for like 20 some years. They were like father and son. Unfortunately, Bohr was a Danish Jew, and Heisenberg was born in Germany and ended up running Hitler's nuclear program while Bohr had to flee to the US. So these two went from having a father and son relationship to having no relationship at all. Many people have kind of examined this, and it actually played a huge role in the development of physics around World War II. Obviously, we don't feel bad for Heisenberg. Some people say that Heisenberg was forced to do it, but that's another discussion. Cool. So these kind of people lay out the foundation, right? Mendeleev's elements, Boltzmann and Curie, atoms. These guys, quantum mechanics. So now we understand that everything that's happening is an arise from just a few atoms interacting with each other. The interaction between single atoms is what leads to all macroscopic behavior. And this idea, I argue, is what changed the world around the 1900s, why things started developing so quickly. right? If we think about computers as an example, the idea of a computer was not new, right? Charles Babbage and Ada Lovelace, who was the daughter of Lord Byron, uh, developed the idea of a computer like 100 years before. And these two had this idea. They built a prototype, but it was so expensive. It was massive. It was really hard to program. And it wasn't a general machine. What made it possible was the new materials that were coming out, the new ideas that were coming out, materials that made electricity possible, really pure wires, made semiconductors. These ideas are what made the technology possible for Alan Turing to re-implement these ideas, plus many of his own ideas, don't get me wrong, still a brilliant mathematician, and was able to actually build the machine that helped the Allies win World War II. And so these materials, this understanding from an atomistic level, led to a boom in technology. This is my end of the history lesson. No guarantee it was right, but it was a viewpoint from a very driven engineer. So now we got to look at our recipe book, right? So now that we know what everything is made out of, now we got to figure out how to actually put it together, right? We have a viewpoint. And so following Mendeleev, these are all the impossible ingredients, all the possible ingredients. We can get rid of a few of them. All of these are radioactive, so not going to use them. And you may be like, whoa, Collin, I really want a toothbrush made out of plutonium. And I would say to you that 1 gram of plutonium would kill you, so maybe not a toothbrush. But for most part, we don't really make anything out of the atoms that are grayed out. We don't really make things out of these things, besides maybe helium. I would argue we don't really use helium as an ingredient in other things. We just kind of put it in things like balloons to make it float up. And the reason we don't use these is because they're noble gases and they don't really react with anything. So we can pass through that. And what we get is this entire periodic table. I've circled some of these, and these are the really common elements. These elements you can find a lot of different places and are super useful and are in almost everything you know. Particular hydrogen is like the milk or sugar or eggs or salt of the universe because it's the most common element in the universe. Oxygen, also really important, also everywhere. Silicon, I think like 70% of the earth is made out of silicon plus oxygen. So, these are the common things. Also, pet peeve of mine while we're on this. If you are ever writing a sci-fi novel, please, please, please use these elements, because what is prevalent here on Earth will be prevalent wherever they are too. And you can identify these pretty easily in a lab. So, new molecules that we've never heard of, totally possible. New elements, less possible. Anyway, so how do we actually develop a material, right? How do we go from having these elements and these resources to what we actually want? Well, we've got our resources. We heat them up. In the process, we burn off gases. Most of the time, the gas we burn off is CO2, and that's where we're going to really have issues with planetary compatibility. And so we burn off the CO2, and then we do some sort of processing, and we get a material. And that's essentially how it works, right? We throw in some stuff, we heat it up, and we look at it. And you're like, whoa, shouldn't the scientific community be doing this better? Yes, we should. But this is the traditional way that we've been developing materials. And I don't mean to say that we just throw in stuff completely randomly. The way it often works is that you have somebody with experience, somebody who's been doing this for like 15 years and really understands the structure and the chemistry of the molecules that form. And they try to guess, or they have a very intelligent guess about if you add more sodium, maybe this oxygen doesn't attach to that carbon, right? And by that kind of understanding, you can start to qualitatively shape the atomistic scale, which should scale up to what you want. And so this is the little flow diagram, right? We have a problem to solve. So we mine minerals, we purify the minerals to a single element, we combine the elements in informed ways that older person, unfortunately, it typically is a guy, which is, due to sexism in science, but that's a whole nother story. We process it in some technique. There are many different ways to process something, and then we check the properties. If the properties are not good, we go back to mining minerals. We start this whole thing over again. If they are good, we just repeat the same scale on an industrial scale. So in a lab, we make maybe a kilogram. On an industrial scale, you make maybe 5 tons a day for a reasonable factory. And here's the problem. Everything in yellow on this slide produces CO2, produces greenhouse gases of some sort. And that is leading to climate change. And that is also fundamentally unsustainable. So here are a few of the worst culprits. Glass is a culprit. For every about pound of glass you produce about 0.5 pounds of CO2. And the worst part about that is that glass is actually one of the least recycled materials. So we're not actually even recycling the glass that we are producing. So every time we have to put out that CO2. Then we have concrete, which is terrible also. There's a 1-to-1 ratio between concrete. Then we have plastic, which produces a ton of CO2 per pound of plastic. That's very dependent on what kind of plastic and what your processing conditions are. And so overall, all materials production makes up between 15 to 30% of all CO2 emissions, depending on who you talk to, which is fundamentally unsustainable. Yeah, okay. The other big number that we should keep in mind is this 51 billion to zero by 2040. We are currently producing 51 billion tons of CO2 a year, and we have to have it to zero by 2040. And so this is the great problem that is facing, I wouldn't even say material scientists, I would be saying all of us. Because the thing is that we want our custom materials. I bet you can't look around and see something that is a natural or found material that was made without CO2. We are so used to specialty materials, especially my generation, right? Oh, we want a screen. Well, they're going to make a specialty glass for that. We want a cup that's a specialty glass. Even the alloys on our computers are alloys specifically designed for the computers. Almost everything we interact with is a specialty material. Paint is a specialty material. Most of our clothes, unless you're wearing all natural fibers, is a specialty material. So we're so reliant on these specialty materials in our daily lives that all produce massive amounts of CO2. And so what we need to do is we need to be able to develop new technology, and we need to be able to progress while also removing the CO2. And this brings to the biggest of all problems. Well, not the biggest. I already said that. A big problem is that this design loop takes 5 to 10 years to be done. It's not something that we can do instantly. So we need to be able to do this design loop very quickly, and with things that aren't traditional single elements that we can't just predict their behavior perfectly of. And as a result, the way we produce materials is not sustainable. Despite this, we've got some really cool applications coming up, right? That we want to be able to design new specialty glasses for, right? I don't know if any of you have it. Flexible screen. Flexible screens are exciting. Augmented reality, quantum computers, memory storage, all of these things are reliant on glass. And all of these glasses are vastly different from each other, which I know sounds crazy, but on an atomistic scale, we use very different stuff. very different sets of stuff to make different kinds of glass. And so you can see that like this is important. We can look at transportation and architecture. Like the glass that out there is getting crazy, right? Like if you've ever been in a Tesla, it's just glass everywhere. Internet of Things, the Shard in London is beautiful. Also glass for energy applications. So it's not even it's not even purely just for aesthetics or things. The windmills made out of on the windmill blades on windmills on big turbines, those are fiberglass. So that's kind of glass spun into a fiber and then pushed together. There are photobioreactors. We have glasses for solar panels. This is John Goodenough at University of Texas, Austin. And he last year turned glass into a battery and was able to use glass as a battery, which he claims is competitive with lithium ion batteries, which is huge. He's also a pretty credible source because he won the Nobel Prize a year or two ago. So, you know, not bad. If I won a Nobel Prize, I wouldn't complain. I'm just saying. Other applications for glass is pharmaceutical packaging, antimicrobial glass surfaces, and bioactive glasses. If you're diabetic or know someone who's diabetic, you know that wounds for diabetics don't close easily. Well, these bioactive glasses have been designed that you can put them in open wounds in diabetics and it will help the wound actually heal in a reasonable amount of time. So these are all huge applications. And here is the most important application, in my opinion. Every month, we are now building a new New York City equivalent in the world. And most of the construction that is happening is not happening in the US or like the UK. It's happening in developing countries. It's happening in India. It's happening in Nigeria is a huge one. And they want just as much materials as we need, and they have more people. And so if we just say stop using all specialty materials entirely, the rich countries are not going to be the ones who suffer. It's going to be the developing countries, and we're going to force them to stay in their current conditions, which is not fair, right? They should have access to just as much information and just as much resources as we do. I'm running a bit fast. I'm talking really quickly. I apologize. I'll try to slow it down for a second. Okay. Yeah, so we can't just stop our materials use because that doesn't hurt us as much as it hurts developing countries that really need it. So what are our options for the future? Well, our options for the future are essentially using the materials that we've already processed, that we already got the CO2, all the things out of. And unfortunately, the only place where we have vast storage of pre-processed materials are landfills. And we need to be able to go through landfills, get the elements out that are valuable to us, and be able to resynthesize them. So essentially, our only option going forward is to figure out how to use trash to produce specialty materials. How are we going to turn trash into that glass on your iPhone? That's our options. And I know that sounds kind of dark, but I believe we can do it. I think there's a lot of really great tech and really great opportunities to do this. So how are we actually going to make it happen? Especially since we don't have 10 years, right? If we start processing everything now, it means we're going to start having new materials in 2030, 2035 that will be rolling off the line, but we'll be using just as much CO2 until then. So where do we go now? To quote Axl Rose, you know, he was the first person to really anticipate this problem. Well, one option is modeling, right? It's very important for us to do modeling because what modeling can do is it can tell us, well, if you have these atoms together, this is the most likely way for them to behave, and these are the most likely properties for them to have. In particular, quantum mechanics only works if you know the exact composition and the exact structure. So that's not going to be super useful. Atomistic simulations are a little better. Analytical modeling helps a lot, right? Because we need to know important processing parameters. But to get all of these things, we can't just rely on these quantum mechanical models. We need to be able to predict the properties of weird trash combinations. And how do we do that? I believe the way forward, and what I do in my research, is using data-driven models or artificial intelligence. And so what I mean when I say artificial intelligence is this. You have an input, you have some black box, and you have an output. And this black box is a function that the computer itself comes up with. And that function is what controls fundamentally the behavior of the predictions. And so once we know that function, we can use it to predict new things. So in our example, we put in different recipes of trash. Maybe you got 3 bottles, glass bottles, 2 cans, a water bottle. You put it in, and what do you get out? Right? That's what we're interested in. We want to be able to say, if I have number of X, number of X, number of X, then I want to know what the property Y, property X, property Z, whatever the properties are. And so if we can build a model like this, then all we have to do is we have to know what properties we want. We have to know our different ingredient possibilities. So if we just change the amount of change the amount of each ingredient, we get different property predictions. So we just keep changing the input until we get an output that accurately predicts and actually accurately gives what we're interested in for our materials. And so this model is the kind of thing that I've been building. And right now, the startup I'm part of, we're using AI. We feed in AI from the outside. We've built AI models. We take trash, literally trash, sorted by category, and we put it in together. We use AI to figure out what the properties of the combination will be. And that's what we're working on. That's where I think the future is. And so if we survive, I have a few predictions. I'm pretty confident that we will. I think the reason we're not right now is because it's not economically favorable to, and I have hope that the government will make it more economically favorable through regulation, but I also have hope that the upcoming generations, our generations, your generation, will invest intelligently into renewables and realize our future. So if I had to make a few predictions for the future, I would say that everything will be pre-processed materials, meaning that everything is going to be just infinitely recyclable. The materials we use will act like the materials we have today, right? We're not going to get rid of any of the functioning materials we have, but on an atomistic scale, they look very different so that we can have them without any of the CO2 emissions. I also think that AI will make huge discovery, AI will make materials discovery and materials predictions really easy going forward so that we can have even more specialty materials. And I expect that for every application, we'll have companies that will make you a custom material. So this is kind of my talk. It's an interesting one, I think. If you have any time to read and you're interested, I know how busy life is, so no worries. I would really recommend these 2 kind of books. I think they're very thought-provoking. I don't necessarily agree with everything in them, but I think that they're the kind of books that really make you think about the future and what it's going to be like. And that's my talk. Are there any questions? I see there are questions. I don't know why I'm saying it out loud. And that's it. Thank you. Okay, so I've got a question. Reducing CO2 production is one way to reduce emissions. Implementing processes which will actively remove CO2 from the atmosphere is another way. Please comment. This is a great question, Will. You're totally right. So when I say the 51 billion to zero, we need to get to net zero. Not necessarily we're producing zero, but we need to be able to be the net amount change from human activity needs to be zero. And CO2 scrubbing or any of these processes are definitely going to be important in that role, but they are also temporary solutions a lot of times, because what you have to do is you have to process that material after it captures the CO2. So you have a material, the CO2 gets exposed to it, then you get either a liquid or a solid, and then you have to do something with that liquid or solid. You can't heat it back up because you're just going to release the CO2 again, which, you know, might not be terrible if we have that down to a low number, but it's also not entirely economically feasible right now. So the scaling of these facilities is really expensive, but those costs are going down, and I hope soon that we're actually going to be able to. I hope soon that we're going to see more of these facilities that are coming up with new creative ways to absorb CO2. Unfortunately, for any private business, while the government isn't supporting CO2 scrubbing, you have to make it very economically favorable, which means that you have to be cheaper than carbon credits, which is hard to do. Is that good? Cool. Thank you. Does your research have a statistical possibility of a Star Trek replicator? I wish. We're a very slow Star Trek replicator. I can put it that way. For me to go from what you want to an actual thing, I can do it. It just takes, with my current AI, it takes about a month. So whatever you want, we can make it happen in a month if you have no budget. So very slow Star Trek replicator. How's that? Thanks for the question, Jerry. If you have any questions, please post them in the question and answer thing, not in the chat. I'm seeing some stuff come up in the chat. Awesome. Cool. Are there any other questions? What is the name of the startup I work at? It's called Glassworks. I wish I could tell you more. We're brand new, so we're still figuring out everything and getting it all together. Awesome. Well, thank you guys so much. If I don't have any other questions, I mean, you're free. I feel like I'm teaching a class again. You are free to leave. Otherwise, I will stick on, and feel free to answer a question about anything. Thank you. I'm glad you enjoyed it. Good. I'm glad you thought it was informative and fun. I promise it's only a little dire. We're gonna have we have lots of opportunities. I believe in us as a species. Okay. Is Glassworks hoping to make custom glass materials or general stuff for the masses? We mostly are working on producing stuff for kind of industrial applications, Jenny. And then I've got Jerry. And Jerry asks, the pandemic has impacted the production of many materials. Has this led to a consideration of more reduce and reuse over recycle? Reduce and reuse is great. The problem is it's less feasible than you think. For instance, the main CO2 impactor in the economy, the main production of CO2 for material production mostly comes from concrete. And you really only get rid of concrete when it's dead, and then we just throw it away. And the number one producers of concrete are the developing countries. So why is it fair for the US to go to them and be like, India, you need to produce less houses? Like that doesn't make any sense at all. So it's not fair to always do reduce and reuse. And then recycling is great, but you're totally right. It's not as efficient. I don't think the pandemic has really shifted this. In matter of fact, we were all hoping that the pandemic was actually going to greatly drop our CO2 emissions from this year, but the numbers just came out over the last year, and our CO2 emissions have only dropped a few percentage points. So we're actually still consuming just as much that is resulting in CO2. And so what we need is we need a new option. We need a reuse slash recycle on an industrial scale, because doing it as individuals will not make the impact that we need. Does that make sense? Or am I just rambling? It's a distinct possibility that I'm rambling. Cool. Thank you.